Dr. Perez, you can go ahead.
Yeah, I think we'd better wait for more 3 minutes. Yeah, I think students are coming one by one.
All right. Are you able to hear me, Lan?
Yes, I can hear
Yeah.
you.
Yeah.
So do you want me to wait a couple minutes or should I get started?
Maybe 3 minutes
Minutes
later.
Okay.
That's fine.
Yeah, we just start on time because just in case some students just come on time.
Yeah, of course.
Thank you.
Okay, Professor Michael. Yeah, I think you can begin your lecture.
Okay, sounds good. And well, thank you everybody for having me here today. I'm excited to share with you a lot of the research that we do down here at Auburn. We have a very unique outdoor testing facility where we get to do a lot of hands-on research. And so I always love the opportunity to share what we do and show you pictures and videos of the really neat research that we get to work on. So I wanted to start by introducing myself and giving you a little bit of background. So my name is Mike Perez. I'm currently an assistant professor at Auburn University. But prior to joining Auburn, I had a little bit of a different route. So I got my bachelor's degree in civil engineering from Florida State University in 2012. And then I came to Auburn and got my master's and PhD. I worked for a short period of time in Atlanta, Georgia, for a company called AECOM, where I did stormwater engineering work. And then I became an assistant professor with Iowa State University in 2017. In 2019, I had the opportunity to come back to Auburn, this time as an assistant professor. So to kind of give you a little bit of idea of where we are, I'm originally from Miami, Florida. So down here, see if you can see my mouse, down here in the southern part of Florida. And then Tallahassee is here where I did my bachelor's. Auburn is here. And then Atlanta. And then I went to Iowa State, and now I'm back at Auburn. So while I was at Auburn as a graduate student, I had the opportunity to visit China and to visit the Beijing University of Civil Engineering and Architecture and teach while I was there. So I spent a summer in Beijing, and I got to work with a lot of great people and a lot of great students as part of the Auburn and BCA exchange program that we had at that time. So today I'm going to be talking about construction stormwater management. And here in the United States, construction stormwater, that's the water that comes off of construction sites during rainfall events, are one of the largest non-point sources of sediment. And so this causes a lot of problems. If you see the picture there on the left, you can see that water is very dirty. It has a lot of sediment, it has a lot of dirt that's mixed in with that runoff. And so that causes issues downstream when that water gets into a receiving water body. So it could be a stream or a river or a lake that gets polluted. And so there's a need to improve the performance of practices that are used on construction sites to help minimize the amount of soil loss that's leaving the site. Here in the United States, every year we have a report card on America's infrastructure, and stormwater received a letter grade of a D. So that's a very bad sign, a very bad grade to receive. And what it tells us is that there's a need to improve the way we manage stormwater in the United States. To give you an idea of how big the problem is, it's estimated that every year there's 80 million tons of construction generated sediment that's being washed into waters of the US. And so 80 million tons is a huge number. It's enough to fill up 5 million dump trucks. These dump trucks would span, if you parked them back to back, bumper to bumper, it would create a 9-lane road from Los Angeles to New York. So a lot of sediment that's leaving our construction sites and washing into the rivers. And so what we do here at Auburn is that we've got an outdoor testing facility that's dedicated to improving the practices that are used on construction sites. And so we're co-located, we're at the National Center for Asphalt Technology. This is a 1.5 mile test track that's used to test pavements. And we have our facility down here at the southeast corner of the facility of the NCAT, and we're called the Erosion and Sediment Control Testing Facility. So this video here just shows you a little bit about the track, and you can see our facility there in the back corner. But the test track is actually used to test different pavements. So they pave the track with pavements from all over the country, and then they run these super weighted tractor trailers around the track to test the durability of the pavement, and they map out cracking, and they map out all the failures that there might be on the track. But our test facility is about 2 acres in size. This is our current facility, or this was our current facility before we did some additional improvements and additions to the facility. And so we've got a variety of test apparatuses, and I'll show you pictures of all of these here. But we can test sediment barriers, we can test skimmers that are used in stormwater detention ponds. We've got a sediment basin we can do research on. We've got 3 channels where we can test a variety of practices that you would use on a roadside channel. And then we also have a rainfall simulator. And on top of all these research apparatuses, we also do a lot of training. And so we've got a variety of training stations throughout the facility where we can demonstrate the proper installation, the proper placement of a lot of these different practices that are used on construction sites. Last year, we actually expanded our facility. So if you look on the top of the picture, you can see this is our our old facility, we now have all of this new area that we just started developing. So we've added about 8 acres to our facility. So now we're about 10 acres in size. So this gives us a lot more capabilities. We have a lot more water that we can use for testing and a lot more space to conduct experiments. When we do testing, what we try to do is mimic or replicate the conditions that you would see on a construction site, but we do it in a controlled environment. And so we pump water in from our storage ponds at a controlled rate to mimic the runoff that you would see on a construction site. And we also introduce sediment into our load, into our water stream, so that we get a sediment laden or a turbid discharge into our test apparatuses. So here, for example, we're pumping in about 1.25 cubic feet per second, and we're pumping in about 50 pounds of soil per minute. And it comes in through this auger and gets introduced into that water, and it mixes in this mixing trough before it goes down into our channel. And so if you were to turn around from this spot where I took this picture, this is what our channel looks like. So this channel is used to test what's called inlet protection practices. And these are used to protect storm drain inlets from receiving sediment or from discharging sediment. So our channel here is about 40 feet in length and 20 feet in width. So it's pretty big in scale. We've got a metal section to help stabilize, to help distribute the flow across the channel. And then we have an earthen section where we can install a practice in native soil the same way it would be done out in the field. You can see here in the back, we've got what's called a total station. This is a robotic total station. It's that yellow piece in the back over here. And we've got all of these lines with flags on them. And those flags are survey points. So before an experiment, we survey the entire channel, and then we introduce that flow, that sediment. And what we're trying to do is measure the erosion, measure the sediment that's captured around a practice. So then we come back after the test and we survey again, and then we can subtract those two surfaces using GIS to determine how much sediment we captured in that channel, or how well that practice performed. So this is an example of what's called a silt fence barrier, and this would be used around a storm drain inlet to try to create an impoundment and to try to capture those heavier soil particles outside of the inlet. We're trying to keep the sediment from going into the inlet because that's what discharges out to our rivers and streams. So you can see with this installation, the practice didn't do very well. You can see the fence is overtopping, it's overwhelmed. The flow is punishing, or it's putting a lot of pressure on that installation. So what we do is we try to come up with improvements. And so this is one improvement that we tried, and it failed. It didn't work very well. Still too much water, putting pressure, hydrostatic and hydrodynamic pressure on the fence. And so what we had to do was use additional reinforcement. So this is the same type of material, that silt fence material, but we put in what is called 2x4s. And this is lumber that is used, it's commonly available and can be used to strengthen the installation so that it no longer, it's no longer overwhelmed by the pressures of the impounded water. And so we also had to develop a dewatering mechanism so that water could exit through the barrier in an efficient manner. The barrier becomes very clogged, and water can no longer pass through it. And so what we have to do is add that dewatering mechanism there in the back. The neat thing about all the research we do at our test facility is that our State Department of Transportation, the Alabama DOT, they adopt these modifications into their standard practice. So for example, that silt fence standard, it's the one down here in the bottom left, that's now the standard practice that is used here in the state of Alabama. So it's very rewarding to see our research go from development, from R&D, all the way to implementation in the field. Another research, another project we worked on here at our test facility was looking at ditch check apparatus or ditch check practices. So ditch checks are used in a roadside channel to slow water down, reduce the erosion on the channel, and then you also get sediment that falls out because you've slowed down the velocity of the water. And so this gives you an idea of our setup, but we've got a 25-foot long metal section, then a 15-foot long or about 5-meter long earthen section where we can install various ditch checks. So here's a video of a practice that failed, that didn't do very well. You can see the stakes, the wooden stakes that hold the wattle in place, they broke because there was too much water upstream. And so what we do is we play around with the installation and we look at different materials to try to make that practice work better. Here's another type of practice. This one's using what's called riprap or stone to create a ditch check. And so that rock is oriented to create basically a dam. And when we run water through it, this is 1.7 cubic feet per second. You can see it impounds about 14.5 feet. And so this impoundment is very desirable because this is what slows down the water. This is what protects that channel from eroding any further. So what we try to do is to improve the impoundment capabilities of these ditch checks by modifying the installation. As an example, here we added what's called a choker stone. So we added smaller rock in front of the ditch check to try to make the practice less porous, to try to choke the riprap, the larger rock, and prevent water from flowing through it so fast. And you can see when we add that rock at the same flow rate, we get 20.5 feet of impoundment instead of 14.5. So we're able to extend that impoundment pool further back and protect more of the channel. We also tried a different installation where instead of using rock, the small rock, we used this filter fabric. This is a geotextile that's wrapped around the rock. And so the idea with a geotextile is that water can no longer pass through the fabric. And so now it has to pass through the top of the ditch check. And so when we do this, you can see we get an impoundment of about 29 feet. So we're able to create we're able to take our original impoundment, which was 14.5, and double the amount of impoundment by adding that geotextile. And so again, this is very desirable because you're protecting a longer piece of that channel. We also looked at different materials that can be used for ditch checks. So this is what's called a silt fence, and we installed it in this V pattern that you see here. And typically this installation gets trenched into the ground, but we tried a method where you would pin it, you would staple it to the ground instead of having to trench it. So it makes it easier from an installation standpoint. It's less work to install it. The other thing we did was, you can see here, we've got a weir that's notched into the ditch check, and that weir allows you to tell the ditch check where to, or tell the water where to overtop the ditch check. So you can use less materials, you have a dedicated spillway, and water doesn't go around the edges, around the sides of the ditch check, which is undesirable. This was in a longevity test. So you can see all the sediment that gets captured in that channel. And we also surveyed this channel. This was after you can see 42 cubic feet of sediment. So about roughly 2 cubic meters of sediment that we introduced. And you can see the amount of deposition upstream, about 38 cubic feet. And in total, that's about 91% retention of all the sediment that was introduced. So that's a very high level of performance from what we're used to seeing. And so this map that you see here, this is generated from that survey of that total station survey that I was describing earlier, that process. So surveying beforehand and then after the experiment. And now you can see that the DOT has also adopted these standards. You can see this is the riprap ditch check that I showed. It's got the geotextile in there. They still use the smaller rock on the outside of the geotextile. And then this is the ditch check practice that has that weir cut in, and it has the pinning mechanism instead of the trenching. And this is one installed out in the field. You can see how big they are, but you can see the silt fence ditch check here with the weir cut out in the center. And you can see how many of these are used along the channel. They use a lot of these on the roadway side when they're doing construction. Another really neat research apparatus that we have at our facility is what we call the sediment barrier test apparatus. And so this apparatus is used to test different types of sediment barriers. These are practices that would be used around the perimeter of a job site to try to keep sediment from washing or leaving the site. And so you can see that here's a silt fence that's installed in our test apparatus. To give you an idea on scale, the installation here is about 20 feet in width, and then the entire apparatus is about 40 feet in length. And so this is designed where we can introduce sediment and water from the top. It goes down that metal section, down that slope, and becomes sheet flow. And then it goes down to the earthen section where we have our practice installed. And then we can take water quality samples upstream, downstream of the practice. We also do surveying before and after a test. And then we collect all of our storm water down at the bottom in that tank. And we can also take measurements in there. We can take flow rate measurements as it enters that collection tank, so we know how fast or how much water is passing through the system. When we develop our flow conditions for our test apparatuses, we're trying to mimic real world flow rates and real world sediment introduction rates. So what we do is we mimic a design storm. In this case, we're using what's called a 2-year, 24-hour rainfall event. That's a storm event that is expected to happen once every 2 years, and the entire storm would last 24 hours. And so what we do is we model that storm through what's called a hydrograph, so we can determine the amount of water to pump into our test apparatuses, so we're mimicking a similar storm event. Similarly, we also model the soil loss that would be expected on a construction site. And so we use what's called the modified universal soil loss equation. And it's a function of the amount of runoff volume, the peak flow of the storm, and then also a function of the soil type, what's called the erodibility factor. It's a function of the topography of a construction site, so the link slope factor. And then we also have what's called the cover management factor and the erosion practice factor. And you can see for this test apparatus, we were introducing about 38 pounds of soil every minute. And our test lasts 30 minutes. So you can do the math and you can see we're putting in a lot of soil during that experiment. Our sand type, it's what's called a sandy loam. And it's about 75% sand. And then the rest of it is a silt and clay. The sand settles out very fast because sand particles are larger, but the clay and the silt are very difficult to remove. And those are the ones we really focus on trying to treat. This is an example of a standard installation, or what used to be the standard installation for a silt fence. And so you can see the close-up image on the bottom right. That's what the silt fence looks like. That's what the material looks like, that geotextile. It gets installed at a height of 32 inches. And there's posts that support the fence upright. Those posts have a weight of 0.95 pounds for every foot, for every linear foot of the post. And those posts are spaced every 10 feet. So the silt fence is trenched into the ground in a 6-inch by 6-inch trench. And then there's fasteners every 2 feet along the top that attach the fence to a wire backing. So there's a wire mesh in the back that supports the entire installation. So this video here shows you the third test into a longevity test. So these are 3 back-to-back experiments that we run on the same installation. As you can see during the third experiment here, the water impound's very high. You can see the T-posts are deflecting. And eventually what happens here is that it breaks the wire in the back, and you have this massive release of stormwater over top of the fence. And so this is very desirable because you can imagine all this water leaving. This is all, you can see the color of the water, it's very polluted. This is going to have an impact downstream. And if there's other practices downstream, this is likely going to overtop those as well. So in our research, we wanted to see how we could improve this installation. We looked at a variety of things. So number one here is we wanted to increase the weight of the post. So we went from 0.95 pounds per linear foot up to a more robust post, which is 1.25 pounds per foot. So it has more metal, more weight per every linear foot. It also has a larger cross-sectional area, so it's a stronger post. We also tested reducing the T-post spacing. So I mentioned that the spacing was 10 feet. We wanted to see what would happen if we went down to a 5-foot spacing, basically adding an additional post in between all the existing posts. We also noticed that we probably didn't need to impound 32 inches of water. So we went down to a different or smaller or shorter silt fence height. We took it down to 24 inches of height. And then we also wanted to test what's called an offset trench. So instead of trenching right at the bottom of the installation, we moved the trench off the base of the silt fence by 6 inches. And this is what that offset trench looks like, where instead of having your post inside of the trench, you move your post back 6 inches. So you have that trench you dig, your silt fence goes in to that trench, and then you backfill it with soil and you compact it. And so this is after compaction, this is on the back side, but now your posts are sitting in native soil that has not been disturbed. And so they have a lower chance of failing because they have more contact in that compact soil. So this test is the same one I showed you in the beginning, except now this is with the improved design. So additional posts, a shorter silt fence, and that offset trench. And you can see comparing this test to that first video I showed you, the silt fence is a lot stronger. It's able to impound the entire height of that runoff, and the T-posts are no longer deflecting. So overall, this is working a lot better. It's slowing down the release of that water, and you're able to capture more soil upstream. I mentioned we capture water quality samples throughout the test apparatus. And so here, this is a cross section of our test apparatus. All these arrows are pointing to a location where we took a water sample. So we're interested in capturing water upstream of the slope. We're looking at the bottom of the impoundment, on the top of the impoundment. We're looking downstream of the silt fence. We're also looking in the catch basin. So in total, we're capturing samples at 5 different locations, and we're capturing samples throughout the experiment. About every 3 minutes, we're capturing samples. You see all the different sample spots here. We use a pump when we're sampling from the bottom of the silt fence. This is the downstream, and this is the catch basin sample point. What these samples allow us to do is to make comparisons on water quality. So here you're seeing in green location 2, in brown you're seeing location 3, and then you're seeing in blue is the depth of the water. So as our test period's 30 minutes, as our test starts and runs for 30 minutes, you can see the impoundment goes all the way up and then it slowly dewaters over time. That's that blue line. And what's interesting here is that you'll notice that the turbidity, or the measure of water clarity, you want it to be as low as possible, as close to 0 as possible. So at the beginning of the storm, it's very high, but you'll notice in that green line, the turbidity starts to go down as the impoundment goes up, which is very interesting. That's telling us that the more water you impound, the lower the turbidity at the surface. So SL2, if you remember, is the top of the water column, the top of the impoundment. Now that brown line is SL3, and you can see that turbidity goes up and it stays high, and it really doesn't drop until after the test, after the 30 minutes. So SL3 is the bottom of the water column. So what that's showing us is that the turbidity, or the water quality improvement that's provided, is from creating the impoundment. It's not through filtration through the silt fence, and that's a very common thought. People think that the silt fence filters, and in reality, what the silt fence does is that it creates a condition where it impounds water and allows the soil particles to fall out through gravity. One of the other improvements we made to this installation is that we added what's called a dewatering weir. And so this weir is made out of plywood, and it gets installed in a break of the silt fence. And that allows water to flow through the top at a dedicated point, so that if you do have a big storm that comes in and overwhelms the fence, it has a dedicated point to overtop without causing total failure. And you can see you add this rock downstream so that it protects the area downstream from scour and from erosion. You also have these dewatering holes so that it allows water to flow through and slowly dewater the fence so that you don't have water sitting in front of the fence for a prolonged period of time. This is a small scale sediment barrier test apparatus that we have at the facility. This apparatus allows us to test just the geotextile portion of the silt fence. So we've looked at a variety of different materials. There's a lot of materials that are available for silt fence. They've got two major classes, what's called the non-woven silt fence, and then you also have the woven type. And these fences or these fabrics all have a different flow rate that they're rated for. So this video here shows you the difference between two of them. The one on the left is a woven silt fence. The one on the right is a non-woven. So the non-woven has a lower flow through. It allows for a greater impoundment, where the woven silt fence has higher flow through and more water passes through. But remember that from our previous study, we learned that creating the impoundment is what's most beneficial to capturing soil particles. So it's not the filtration, it's the impoundment. So the one on the right, you would expect to work a little better. This table here shows you a comparison of the different practices or the different fences we looked at. So you have the non-woven fabric and you have the two types we tested. You also have the three woven fabrics we tried. The interesting thing here is that if you look at our average flow rates, and these are gallons per minute for every square foot of fabric, you'll notice that the non-woven has a much lower flow rate than the woven fabrics. But the interesting thing is that you can see the published flow rates, this is from the manufacturers, is a lot higher than what's actually being provided. So for example, this needle punch non-woven, the manufacturers say 150 gallons per minute for every square foot, and we were only seeing 1.5. So a very big difference between what's published and what actually occurs in the field. And that's because when they test those products, they test them with clean water, not with sediment-laden water. But we know in construction sites, we can expect sediment-laden water, not clean water. We also looked at sediment retention in that apparatus. So we were introducing water and sediment. We wanted to measure how much sediment was captured upstream. And you can see that the non-woven fabrics had about an average of 97 and 98% sediment capture by weight. And the woven fabrics had anywhere from 87 to 94% capture. So both fabrics actually perform very well from a sediment capture standpoint, but the non-woven performs a little better. And again, that's because of the impoundment capabilities of the fence, of the fabrics. This is another research apparatus that we have. This is called a rainfall simulator. This rainfall simulator has sprinklers on these riser trees that mimic a storm event. So this shoots water out, it's all pressurized, and it allows us to test a variety of different products that would be used to control erosion on the site. So this slope here would have different products installed, or would have just bare soil. We're doing a control test. And we can mimic a storm event by applying rainfall. So this is a 2-inch per hour rainfall intensity. You can see how much rain that produces. But then we also go up to a 4-inch per hour. So here's the 4-inch. And then we also have a 6-inch per hour storm event. And so in total, these three events we do for 20-minute intervals. So we do 20 minutes of 2-inch, 20 minutes of 4-inch, and 20 minutes of 6-inch. So you get an hour-long storm event. And during that hour, it's equivalent to the 500-year storm here in Auburn. So this is a lot of water coming down in a short period of time. So what we've seen here with this test apparatus is that we're able to measure the amount of sediment loss by not protecting your slope. And then we come back and we protect the slope and see what difference there is in sediment loss. So you can see for this sandy loam type soil, we had about 700 pounds of soil loss through one of our test sequences. And this is comparing it to a loam soil where you have 2,200 pounds of soil loss. So very different amounts of erosion. So the soil type that we build on also has a lot to do with how much soil or how much soil loss you have on a site. Here's another test apparatus. This one is designed to test what's called catch basin inserts. And so this was done for an Ohio DOT project, but we were looking at evaluating these bags or these inserts that go into the storm drain catch basin. So the way this system works is, again, we pump water and we pump sediment through this pipe, and then it hits this metal section and goes into the catch basin. And so this is what the inserts look like. So this is an insert that gets fitted into the storm drain inlet. It's made out of a geotextile, and the idea is to act like a filter to try to capture runoff as it goes into the inlet. So here's some testing that we did. You can see we had a low, medium, and high flow rate. So our flow rate went all the way from 0.06 feet per second up to 0.18 cubic feet per second. And what we learned was that these bags only retain about 50 to 62%, 65% of the amount of sediment we introduced, which is not very good. From a total suspended solids, it only captured between 49 to 57%. And it had a lot of bypass through those openings because they're not able to pass that high of a flow rate. So these did not work as well as manufacturers claimed, and so they're not being used very much, not being adopted. This is our sediment basin test apparatus. So sediment basins are used at the bottom of construction sites to try and capture and detain all the runoff before it leaves the site. So this becomes the final point, the final location where you can treat that stormwater before it leaves the construction site. And so we were testing a variety of different setups within the basin. We were looking at these baffles that are installed. These baffle systems here are installed perpendicular to the flow. That's used to slow that water down, to spread the flow across the entire width of the basin. We also tested practices upstream and downstream, trying to improve the way the basins work. Another thing we get into is product evaluation. So we work with different manufacturers to test their products in our test apparatuses and see how well they work. And we can work with research and development on their side to help them improve the product, help them understand the way it works, help them modify it to make it perform better. We also do a lot of training and outreach at our facilities. So we'll do hands-on training where we set up our entire site to do demonstrations, and we teach professionals in the industry how to install these practices and how to properly place them and maintain them, inspect them, so that they work to the best of their capabilities out on a construction site. So this is one of the more fun aspects of what we do, is to actually share the research we do with the industry and help them adopt the practices that we've developed. And so I mentioned that our facility is undergoing some expansion. So the area in red was our original facility, and then the area in yellow is our proposed expansion. And so we've developed about a third of that yellow area now with our expansion. You can see we did some construction last summer working on this facility and expanding it. We added several ponds to the new area. We added some new testing locations and new testing apparatuses. And so this is a lot of fun to be able to do all this construction, do all this work, and expand our capabilities. So here's another picture showing you this newly expanded area. You can see our new storage ponds. We have an upper storage pond and a lower storage pond. And between the two, we have about 3 million gallons of additional storage now in stormwater that we can use for our test apparatuses. We're installing new rainfall simulators. We also are doing work for the Iowa DOT, looking at a channel and sediment basin setup. And so all of these new apparatuses are a lot larger than our original apparatuses. And you can see that was our construction team last summer. But to give you an idea on some of these test apparatuses, this is our Iowa DOT sediment basin. And so the way this works is that we'll be pumping water in from the storage pond into our test channel. We'll be introducing flow and sediment at the mouth of that channel. We'll be testing a variety of practices like rock check dams. We'll have baffles installed in the basin, and we'll also have a skimmer or dewatering mechanism in the back. And so this will allow us to make improvements to the current practice or the current setup that the Iowa DOT does. And so here's a schematic showing you the setup that we've created. You can see this channel is 200 feet long, so about 66 meters. So it's pretty large in size. And you can see the cross section of the channel, about 43 feet across, 10-foot bottom. And then the side slopes are 3 to 1, 3.5 to 1. And then in total, it's about 5 foot deep. We're also looking at a new research with our rainfall simulators. So we're going to be varying the configurations, different slopes, different soil types, looking at topsoil versus clay, loam, and sand soils. And the idea is to develop design-based guidance for better use of different erosion control practices. We're also working on flocculants. So these are chemicals that are used on construction sites to try to capture soil particles, the smaller soil particles, make them larger, and help them fall out of suspension at a quicker rate. So we're developing guidance for the use of these flocculants on construction sites. We're also doing some really cool things with UAVs. So we've got a project where we're doing deep learning implementation. We're using these on construction sites to identify where these stormwater practices are installed and be able to map them out. So this is a very cool research project. We're using drones, we're using surveying, we're using deep learning methods to try and map out a construction site and inspect the construction site using a drone. So with that, I just wanted to share some of the work that we're doing here, some of the hands-on research we're doing, and I'll open it up for any questions. Feel free to submit questions through the chat, and I'll be happy to entertain those and answer those for you.
Thank you so much for the lecture by Dr. Perez. And the students usually will send out their questions by the side of the question and answer part. That button hasn't shown up in my, it can be accessed through the more function by the side of share screen. So when the student asks the question, it will pop out by itself, I think. Yeah. And students, you're welcome to ask any questions. Yeah, here it comes in the chat box, Dr. Perez.
All right, so go ahead, Lan. Would you like to read the question? You want me to read it out loud?
I thought they asked the students to ask the question in the chat box. Are we seeing the same message?
So I see a question came in asking if the pollutants separated from the soil can also be transported to the receiving water body if they are tritium nuclear wastewater containing radioactive substances. Wow, so that would be a very concerning pollutant to have on a construction site. Typically, our concern is soil, and if we can capture soil, we're saving the downstream water body from pollution. Soil creates a lot of problems. It smothers the areas where fish nest. It makes the water very cloudy to where fish can no longer see or can't breathe. And so that's our main concern. It's soil. If you had other types of pollutants, sometimes we're concerned with nutrients such as phosphorus and nitrogen. Those are not captured as well by the practices we use. You actually need to have a chemical reaction to try to capture those. You can capture some phosphorus because it tends to sorb or attach to soil particles, but you're not capturing all of it. And if you had some kind of radioactive substance, I would imagine that what we're doing would not be able to slow that down or capture that at all. So you would need an additional type of practice to try to capture that. A question came in on how you can contact me. So I've got my email address here, mike.perez@auburn.edu. Feel free to send me questions or reach out to me. I also invite you to check out our webpage, esc.auburn.edu. We've got really cool information, great videos in there as well of what we do, and you can learn a little bit more about the research that we conduct out here. Question: what is the role of geographic information science in soil erosion management? That's a great question. So when it comes to soil erosion, one of the challenges we have is sometimes we just want to know how much soil erosion are we having. So one way that we can use geographic information science, or GIS, is to map out different areas on a construction site. And what we've done is we've mapped out before a storm, after a storm, and try to quantify how much soil loss has occurred because of the storm event. So that's one application. We also use GIS to map out where practices need to be installed. So for example, on the picture you see here, this is a construction site that has a variety of practices installed. And so you can see in the center line of that channel, or the center line of this road, you've got all of these different ditch checks installed. And so just in this picture, there's probably 50 of them. But this construction site is 12 miles long. So it's a very large construction site where there's thousands of these installed. And so we use GIS to map out the placement of all of these, the location of all of these, so that the contractor knows where to install them. So that's another way you can use GIS. And then in our research, we use GIS when we're surveying our channels or different test apparatuses before and after a simulated event, so that we can measure how much sediment is captured upstream of the practice or downstream of the practice. So we use GIS in everything we do, and it's a very important tool in our research and in the work we do out in the field. That was a great question. So I don't see any other questions in the Q&A box. Feel free to send them in, or feel free to reach out to me again on my email. I'll be happy to answer any additional questions or share with you any additional information that I can provide. Let's see, I got a question here. It says, in the rational utilization of rainwater, can ecological water supplement be carried out? And what about the silt in rainwater? So I'm not sure what is meant by the first part of that question. Can ecological water supplement be carried out? And when it comes to silt in rainwater, so typically here in the US, the rainwater is free from pollutants. The pH might be a little off. Sometimes we can have what's called an acid rain, where the pH is lower than neutral. But typically there's not a lot of material in the rain. It tends to be pretty clean. It's not until those raindrops hit the ground and hit bare soil that we have silt leaving a construction site. But if you can rephrase that first half of the question, I'll be happy to try to answer it.
We can wait for 1 more minute for that student to rephrase if he or she is good to go, and after 1 minute, we can go ahead and close the lecture. Yeah.
So while we're waiting, I'd just like to thank you all for the invitation to present today. I really appreciate the opportunity to do that and to share my research with everybody. As you can see, I'm very passionate about the work we do, and we have a great team of students that work with me and work in our team to do this type of research. And I've got graduate student positions that come up every year. If you are interested in this type of research and this type of work, send me an email. I'll be happy to connect with you and share with you more information about the work we do. So thank you again for the opportunity.
Okay, I think Dr. Michael, I think this is really a nice presentation, just like the students said. Thank you again.
Yeah, thank you.
Thank you. Thank you so much for your time and support.
You're very welcome.
And I think it's time for the end of this lecture. And thank you all for participating. And tomorrow there will be another lecture starting from 3 p.m. And the email will be sent out soon for the international students. And the Chinese students pay more attention for the WeChat group notice. Thank you. And thank you again for Dr. Perez. Bye.
Hey, Michael, and I look forward to see you in the near future.
Yeah, absolutely.
Bye-bye.